Greetings to you. After we have discussed about the various electronic transitions, we will continue our discussion on the prediction of the molecular absorption peaks. Here we had stopped in the last class, that is, I had told you that the electronic transitions are of 4 types, and these include sigma to sigma star, n to sigma star, n to pi star and pi to pi star transitions. Basically, you can imagine this in terms of organic compounds, where you have a sigma single bond, double bond and elements functional groups with non-bonding electrons, that is spare electrons. And so sigma to sigma star transition essentially implies that it is a saturated compound. There are no unsaturation, no pi bonds and nothing like that. And then n to sigma star is a transition of electrons from compound from functional groups containing oxygen, nitrogen, phosphorus, etc. These are non-bonded electrons present on single atoms. If you look at the electronic structure of ammonia or something like that, you will immediately recognize that there are 2 non-bonding electrons on nitrogen. Same thing is true with oxygen, which has 2 lone pair electrons. Similarly with sulfur, etc., and those are the non-bonding electrons, and corresponding transition it can take place only from n to sigma star. So, the non-bonding electrons are designated as n, and then where compounds where there are double bonds, that is where pi bond is involved, we expect pi to pi star and n to pi star transitions. So, from transition from pi to pi star would be of higher energy than n to pi star, because they are bonded. Pi to pi star transitions, the electrons involved are bonded, whereas n to pi star transitions are not involved in bonding. So, the relative transition energies also we had discussed in the last class, that sigma to sigma star should require very high energy, n to sigma star should have slightly lesser energy, but this will have higher this requires higher energy in terms of kilocalories or electron volts from then pi to pi star, and pi to pi star transition would be requiring higher energy than n to pi star. So, these are the different kinds of transitions we expect. So, the absorbance or the optical energy, optical density of a molecule absorbing in ultraviolet or visible region depends on the molecular structure. Just I was explaining to you that sigma to sigma star, pi to pi star, etc., these are all molecular structures basically representing different bonds, sigma bond, pi bond, non-bonded electrons, etc. So, it is obvious that absorbance or optical density of a molecule depends on the molecular structure. For example, a saturated compound cannot show you pi to pi star transition, and a compound which does not have lone pair of electrons cannot give you n to pi star transitions or n to sigma star transition. It is very simple to understand, but the whole absorption process depends upon Beer-Lambert's law, which states that absorbance A is equal to logarithm of I 0 by I, that is also represented as epsilon BC, EBC, where here you should recognize that I 0 and I are the intensities of the incident and transmitted radiation, and E is known as molar absorptivity, B is the path length, and C is the concentration expressed as gram moles per liter. We will come back to this again during our discussion in this course, but for the time being later we will do the derivation of this, but for the time being what I want you to understand is the absorbance or the optical density of a molecule depends upon the initial intensity and final intensity. That is, a substance has to pass through, assuming you have a substance captured in a space volume like this, and then a radiation is coming and passing through the absorbing molecule, and what comes out. So, that is represented by I0 initial and I is the final. So, part of it is getting absorbed by the molecule, and that ratio, logarithmic ratio of that, of the intensities of the incident and transmitted light is given by epsilon, that is molar absorptivity, that is depends upon the molecular structure, path length, that is size of the absorbance, size of the molecule, and that is path length, and C is the concentration. If the concentration is more, absorbance will be more. So, we will come back to this derivation of this later, but for the time being what I want you to concentrate is how it is related to the structure of a molecule. Basically, molar absorptivity is a functional of the size of the molecule. If the size is bigger, absorbance will be higher. So, it depends upon the cross section of the molecule, that is number 1. Number 2, again it depends on the transition probability. What are the possible transitions expected from a given molecule? Suppose it is a saturated molecule, we can easily expect that it will be only, it will give you only sigma to sigma star transitions. Suppose it has got a pi bond, unsaturated compound, ethylene, propylene and so many other compounds like that, then you can expect sigma to sigma star as well as pi to pi star transitions. Then suppose it contains nitrogen or something, you would expect sigma to sigma star, pi to pi star, n to pi star transitions as well as n to sigma star transitions. So, the total structure, the actual number of transitions depends upon the probability of the transition. That is, more number of transitions, higher would be the intensity. For that, the energy of the incoming radiation should coincide quantum mechanically with the energy difference between the two excited states. Those two excited states transition energy is determined by the difference between the energy level. If the incident radiation is matching with that quantum mechanically energy wise, then transitions will take place. So, it is always a question of probability. So, we have a relationship something like this, minus delta P by P is given by 1/3 of G concentration, and then N is the number of molecules, A is the molecular cross sectional area, and B is the path length delta B, and that is converted into meters or something like that. So, here the decrease in the intensity minus delta P by P represents the corresponding decrease in the intensity of absorption. P here you have to always assume that I am going to use P and I as the incident energy for the throughout our this course. I am using them interchangeably, I0, P0 and P like that. So, here I have written P and it is the probability now. So, minus delta P by P is given by 1/3 of the 1/3 of all these expressions, 1/3 G C N A delta B by 1000, where N is the Avogadro's number, because we want to express it in terms of molecular weight, and A is the molecular cross section, how big is the molecular size, and 1/3 is a statistical factor, because any molecule if you take, it will be having a 3-dimensional structure in space. So, since our direction of the incident radiation will be only in one direction and measurement also will be only one direction, we take it as 1/3 probability, that is a statistical factor, and C is the concentration, G is the statistical weight factor, which I was explaining to you that it has to match with the probability, and B is the path length. So, this expression, if you put all these numbers, Avogadro's number, you know, concentration we can find out for a given molecule, G is the probability statistical weight factor, B is the path length. If we put all these at the optimum level, then what we end up is we integrate and insert the numerical constants, we get an expression something like this, logarithm of P naught by P1. Again these two I am interchanging, instead of P naught by P I have written P naught by P1 corresponding to a particular output, and that I have to after taking out the constants on the left side I get BC constant, these two are constants which corresponds to 0.87 into 10 raised to 20 and P into theta. Since many organic molecules have a cross sectional area of about 10 angstroms. So, epsilon, maximum epsilon, that is molar absorptivity, what we get is approximately 10 raised to 5. This I want you to remember that this is the optimum, this maximum concentration which corresponds to the minimum detectable quantity. Okay. So, if the absorption coefficient is very high, how much you can get maximum? 10 raised to 5. So, that determines the minimum detectable quantity in a given spectrophotometer. So, this 10 raised to 5 is our limit. I have never seen in my career more than 10 raised to 5 at any time. It may be 5 into 10 raised to 5, 10 into 10 raised to 5 like that, but 10 raised to 6, 10 raised to 7 I have not seen. But if it were so, we would have been able to determine with spectrophotometry nanogram materials. Now, this restricts us to parts per million or parts per billion, that is microgram and nanogram, sub nanogram basically. So, the highest known molar absorptivities are of this order, and that is 1 lakh and above are considered as strong band. So, below 1000 are low intensity. They may be either quantum mechanically not observable, or it could be very weak band also. So, saturated hydrocarbons, alkyl groups, alcohols and ether groups, they do not absorb in 200 to 1000 nanometer range. Why? Because there are no pi bonds, no only sigma bonds. So, all these saturated hydrocarbons, alkyl groups, alcohols and ether, all these things 200 to 1000 nanometer range they do not absorb. So, if all the valence bond electrons are involved in single bond transformation, single bond formation, we have only sigma to sigma star transitions expected. So, owing to high energy requirement in such cases, if at all if they occur, it will be in the vacuum ultraviolet region only. So, the only exception is cyclopropane, which absorbs at 197 nanometer, which is in the purview of a spectrophotometer, normal laboratory spectrophotometer. The only thing that can be detected sigma to sigma star transition is cyclopropane. So, coming to the next point, second point in this slide, what we see is compounds containing non-bonding electrons on oxygen, nitrogen, sulfur or halogens show n to sigma star transitions in the ultraviolet region. Why? Because oxygen, nitrogen, sulfur and halogens, all these have non-bonding electrons. Now, between n and in this slide you can see between n and sigma star there is an arrow at the bottom. Actually, this arrow should be in between the two. Due to some technical problem, it has moved a little bit. Same thing has happened between sigma and sigma star also. you can see here at the bottom the arrow, but I want you to note it down. We will try to correct it if possible, but let me see. So, such coming back to this slide, such compounds will show CH3OH, for example methyl alcohol, it shows a sigma to sigma star transition of 183 nanometer in a spectrophotometer. What is the epsilon value? It is 150. That means the intensity of the peak is very small. Okay. So, when the intensity is very small, you may see it as a peak or only as a small hump in the spectrum. So, look at the next slide again, methyl chloride. What is the structure of methyl chloride? I can show you this. I was explaining to you that CH3 Cl cyclopropane I had explained to you. This is nothing but CH2 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 and this is CH2. These are the sigma bonds. So, what we expect? Only sigma to sigma star transitions. So, this is occurs at 197. Similarly, in CH3OH, this is what we were discussing. Now, this oxygen has two lone pair of electrons which are not bonded. If I had to write the structure of this, I would write like this. This is CH3, sorry, that is a single bond. This is H. So, this is CH3OH, there are two lone pair of electrons here, and here I can expect between carbon and hydrogen, three carbon and hydrogen atoms, and between carbon and oxygen, oxygen and hydrogen. All these can give me sigma to sigma star transitions. That is one set. Second set is there are two lone pair of electrons on oxygen, I have written at the top and bottom. So, I can write N to sigma star. This transition also is expected, but N to pi star, no, not possible because there is no pi bond in this structure. Okay. So, we go back and then we go back to the slide compounds. So, here this is what I was explaining to you, methyl chloride and CH3OH will give you 183 nanometer and 173. These are in vacuum ultraviolet region. They are not in the normal instruments available in the laboratory, and if you look at the epsilon value, you will get 150 as one value for CH3OH and only 100 as the molar absorptivity. I have already explained to you that molar absorptivities of below 1000 are absolutely useless. You may just see a small hump or you may not see anything. A lot of people have studied how to correlate the structure of an organic compound and the expected peak for a given compound, UV visible UV, or it may be visible or anything like that, and these are available in the form of some empirical rules known as Woodward-FIESER rules. These rules are mostly applicable for organic compounds, but not aromatic. Please remember, because in some of the slides I may show aromatic structure, but aromatic structure is not accounted for in these Woodward-FIESER rules. So, they have formulated empirical rules for the substances containing single bonds, double bonds, pi bonds, and then non-functional groups containing oxygen, nitrogen, etc. How the actual wavelength where it can be expected. So, this is they had examined more than 50,000 organic compounds like this and formulated these rules. For this reason they were awarded a Nobel Prize. So, in general what it actually represents is a system and you have to determine the structure. So, if you have a parent butadiene structure, that is a CH2 double bond CH single bond CH, then double bond CH2, something like that. We will do a lot of problems based on this. So, parent butadiene will show a basic peak at 217. Now, if the diene is in a ring separated by a single bond, that means two double bonds separated by a single bond, that is known as diene. Okay. If both such a structure is inside a ring, then it is known as homoannular diene. We will see the structures later, but for the time being I want you to remember these structures so that we can look at it in a different way. So, parent heteroannular diene is one double bond is inside a ring and one double bond is outside a ring. And alkyl substituent, there are number of organic substituents. Any alkyl substituent or a ring residue will add 5 nanometers to the basic structure. And if there is an exocyclic double bond, you should remember this. An exocyclic double bond is a double bond attached to a ring outside. That means a double bond is attached to a ring which is double bond should be outside the ring. So, that is one that will add every exocyclic double bond, if it is there, it will add about 5 nanometers to the base value, that is 217 or 253 or 214. These are the basic structures. So, if there is an O-alkyl substance, then it adds 6. Every extended double bond, that adds 30 nanometers. S-alkyl adds 30. Chloride bromide substituents, if they are there, they will add about 5, and N-alkyl will add about 60 60 nanometers to the expected peak position. So, similar structures have been reported for alpha beta unsaturated compounds which include aldehydes and ketones. So, if you have an alpha beta unsaturated say a 6 ring or alkylic ketone, what we mean is a double bond separated by a single bond and attached to a double bond. So, double bond, single bond, double bond, single bond, if like that, the structure should be there in that. I will try to show you in the next few seconds, next few minutes what these structures mean, but the basic structure should have a peak at 215. Suppose it is a 5-membered ring, then the base value would be 202. Suppose it is alpha beta unsaturated aldehyde, then it is approximately 207. See how much energy they have put in finding out the base values, that is important. So, if it has got a double bond CH and COX, where X is an alkyl group or X is OH group or OR group, then the base values will change accordingly. So, for exocyclic double bond, which I have already explained to you, that a double bond attached to a ring is known as exocyclic double bond, and that is 5 nanometers. It will add endocyclic double bond, it will add 5, extended double bond is again 30, alkyl group or ring residue at alpha beta positions is the 10 and 12, and if it is a homodiene, then it is 39 nanometers. Okay, homoannular diene, that means both double bonds inside a single ring is known as homodiene. Okay. So, compounds containing only sigma and pi bonds. Suppose there are no n electrons, no oxygen, no sulfur, no chlorine, no halogens. Example is butadiene. This is a conjugated diene, which I had explained to you earlier in my previous slide, that is butadiene, parent butadiene or cyclic conjugated diene. So, this is the structure of butadiene. this represents CH2, CH, CH2, CH, CH2. Okay, CH2, CH, CH, CH2, and this is a hexatriene. This is 3 double bonds, double bond, single bond, double bond, single bond, double bond. So, these are the examples of dienes and polyenes. Okay, they contain only sigma bond and pi bond. So, the base value for this according to Woodward-FIESER rules is 217 and epsilon value is 21,000. For the triene it is 256 nanometers and the epsilon value is 22,400. So, what do we derive, what information we derive from this information? We derive that a butadiene will show an absorption peak at 217 nanometers and its epsilon value is 21,000, that means it shows a very sharp peak at 217. Similarly, hexatriene will show a very sharp peak at 256 because the molar absorptivity is very high. So, I have put together some more examples for you. That we will discuss in the next module. Okay. Thank you.